In today's video, we're going to look at systems of linear equations and how to solve them. Now, this should be a review for many of you from intermediate algebra. Ultimately, the goal of the next several videos is to relate systems of linear equations to matrices and develop a quicker, simpler method of solving systems of linear equations by using matrices. Okay, so a linear equation in n variables labeled x1, x2, so on and so forth, xn, has this form, right? a1, x1 plus a2, x2 plus so on and so forth plus an, xn is equal to b. Each of the a's, so the a1, the a2, the an, these are called the coefficients. And they are simply real numbers. The b term is called the constant term. And it is also a real number. a1 is the leading coefficient, and x1 is the leading variable. Right. Examples of linear equations: 3x plus 2y is equal to 7. 1/2 x plus y minus pi z is equal to the square root of 2, right? Remember that pi is a constant, not a variable. Sine of pi times x1 minus 4x2 is equal to e squared. Remember, sine of pi, again, is a constant that evaluates out to something. And e is also a constant. So e squared would be a constant, right? So these three all fit the form of 1. Right up here, 1. These three are not linear equations. We call them nonlinear equations, right? So x, y plus z is equal to 2, right? This is not linear because you have a variable times a variable, x times y. E to the x minus 2y is equal to 4. This is nonlinear because of this e to the x term. That's an exponential term, not a linear term. Sine of x1 plus 2x2 minus 3x3 is equal to 0. Nonlinear because of this sine x1 term, right? Again, this is a trigonometric term. You're taking the sine of x1. It's not a linear term. Right, so a solution to a linear equation in n variables is a sequence of n real numbers, s1, s2, so on and so forth, sn, that satisfy the equation when you substitute the values into the equation. That is, when you substitute x1 equals s1, x2 equals s2, so on and so forth, xn equals sn into the equation itself. The set of all solutions of a linear equation is called its solution set. Right, there are several possibilities in a solution set. You could have it being empty, meaning there's no solution. You could have it as a single solution, so there's only one sequence of values that satisfy the equation. You could also have an infinite number of sequences that satisfy the equation, right? So an infinite set. The next example, we're going to solve two linear equations. Right? We will solve first x1 plus 2x2 is equal to 4. Right? So to do this, right, this means that x1, 4 minus 2x2. right? Now, in this case, what we're saying is the variable x1 depends on the variable x2, right? But the variable of x2 can take on any value. It is independent. All right, so therefore we're going to say the solution set, and remember it is a set, so we need to use set notation. All right, we'll say 4 minus 2r, comma r, such that r is some real number. Right? Again, since x2 is the independent, it's independent of anything, we can set it to be any value we want. We're going to say it's some value r. Then x1, which depends on the value of x2, specifically, it'll be 4 minus 2 times whatever value we chose, in this case, r. Solving number 2, done in a very similar fashion. In this case, I'm going to solve for z, right? So add z to both sides, subtract 3 from both sides. Z is equal to 3x plus 2y minus 3. Now notice here, right? We have z dependent on x and y. X and y are independent. So they can take on any value we want. Right? So let's say x will be r. We'll say y will be t. Then z would be 3r plus 2t minus 3, such that r and t are both real numbers. Both of these were infinite number of solutions. Right? So a system of m linear equations in n unknowns, or simply called a linear system, can be written in this form. Right, we'll call this system 2, where each of the aij are real numbers, and each of the bi's are also real numbers. Right, so aij is said to be the coefficient in the ith equation associated with the jth unknown. And bi is the value that the ith linear expression is equal to. The n vector, or the column matrix S1, S2, so on and so forth, Sn, is called once again, a solution of the linear system if substituting x1 equals s1, x2 equals s2, so on and so forth, xn equals sn, into all of the equations, results in each equation being a true equality. The set containing all such solutions is once again called the solution set of the system. And again, 3 possibilities. You could have the solution set being empty, meaning there is no solution to the system. You could have a single solution to the system, or you could have an infinite number of solutions to the system. Now, if the system 2 has no solution, the system is said to be inconsistent. If system 2 has a solution, the system is said to be consistent. If 2 systems have identical solution sets, then the systems are said to be equivalent. So 2 systems that have the exact same solution set are equivalent systems. A property, theorem 1, number of solutions. This was already mentioned. For a system of linear equations, precisely one of the statements below is true. The system has exactly one solution. The system has infinitely many solutions. The system has no solutions. So for any given system, only one of these three statements can be true. In other words, given any system, it'll have either one solution, an infinite number of solutions, or no solution. To find a solution to a linear system, we use a technique that is known as the method of elimination. In this method, we reduce the given system into a simpler equivalent system using the following three operations. Interchange any two equations, multiply any equation by a non-zero constant, add a multiple of an equation to another equation. Right? Typically, in the method of elimination, the goal is to eliminate as many variables, as many unknowns as possible. This puts the system into a simplified form. Once we solve this simplified system, we then use back substitution to find the remaining unknowns. We have three examples, one for each of the three statements above. We'll look at one system that has only one solution, one system that has no solution, and finally one system that has an infinite number of solutions. Starting with a system that has only one solution, we will solve this system. Now, for convenience, what we will do is label each system, or label each equation in the system, right? So, equation 1, equation 2, equation 3. Well, the easiest unknown to eliminate right now would be x, right? Look, because the first equation has a single x. So it's extremely simple to get rid of it. To do that, we can just add equation 1 to equation 2. This will result in the x's dropping out. We'll have negative 2y plus 3y, which is just y. We'll have 3z plus nothing, and that is equal to 9. Then we can add negative 2 times equation 1 to equation 3. Right? We'll have negative 2x plus 2x, that gets rid of the x's. Then we have 4y minus 5y is negative y. Negative 6z plus 5z is negative z. Then we have what? Negative 18 plus 17, which is negative 1. So this gives us a new system. Specifically, this gives us the system y plus 3z is equal to 9, negative y minus z is equal to negative 1. Again, let's label these equation 4 and equation 5. From here, we can either eliminate y or z. It would appear the easiest to eliminate would be the y's. Right, we have equation 1 has a positive y. Equation 2 has a negative y. Simply by adding these two together, we can get rid of it. So that's what we're going to do. Equation 4 plus equation 5 yields 3z minus z, which is 2z. 9 minus 1 is 8. We get 2z is equal to 8. That's very easy to solve. We get z is equal to 4. I'm sorry. Yeah, z is equal to 4. This should not have been 9, though. My apologies. It should have been 9 minus 4 is 5. Right, so that should have been y plus 3z is equal to 5. Then 2z would equal 4. And so z is equal to 2. Now, what we can do, take z equals 2. And let's plug it into equation 4. Right? We can plug it into either 4 or 5. It doesn't matter. 4 looks like the easiest to work with. Doing this, we're going to get y plus 3 times 2 is equal to 5. Right? That means that y plus 6 is equal to 5. Or y is equal to negative 1. Now we look at the original 3, 1, 2, and 3. Well, equation 2 only has a x and y in it. So that'd be the easiest one to sub back into. So let's go ahead, take y equals negative 1, plug that into equation 2. Again, you can use 1 and 3. It's just you'd have to then also plug in z equals 2. We'll get negative x plus 3 times negative 1 is equal to negative 4. This means that negative x minus 3 has to equal negative 4, or that negative x is equal to negative 1, which means x is positive 1. Therefore, we have a single solution. Right? So our solution, x is 1, y is negative 1, z is 2. Right? And it needs to be written as an ordered triple in this case, right? So if you have a system in n unknowns, your solution needs to be represented as an n tuple. Let's now examine a system that has no solution. Right? So we're going to solve this system. Again, for convenience, we'll label each equation. Right? So equation 1, 2, and 3. Here it looks like it's simple enough to eliminate any of the 3 variables first. Let's start with eliminating x1. Right, to do this, we can add negative 2 times 1 to equation 2. Negative 2 times equation 1, I should say, to equation 2. This will result in 6x2 minus x2, which is 5x2. Then we get negative 2x3 minus 2x3 minus 4x3 is equal to negative 2 plus 2, which is 0. Then if we take negative 1 times equation 1 and add it to equation 3, what we get, again, the x1s drop out. So we get 3x2 rather, plus 2x2 is 5x2. Right, then we have negative x3 minus 3x3 is minus 4x3. Negative 1 plus negative 1 is equal to negative 2. Now, right here, we can stop, right? This results in what is known as a contradiction. If you look, both terms on the left are identical, yet they are equal to 2 different values. That is like saying 8 is equal to 8 and 8 is equal to 7. That is nonsense. This means that there is no solution. Right? So represent it as the empty set. S is the empty set. Right? And now let's examine a system that has infinitely many solutions. Right? Again, for simplicity, let's just go ahead and label each equation. Equation 1, 2, and 3. Well, we can look at this. And again, it's fairly simple to eliminate any of the 2 any of the three unknowns. So again, let's start by eliminating the x1. Right, we can do this simply by taking equation 2 and adding it to equation 3. Right, x1 minus x1, that drops out. We're left with 0x2 plus 3x2, negative 3x3 plus no x3, and then negative 1 plus 1 is 0. Then we can write this as equation 4. We have a new system, right? So let's actually do that. We get a new system. We're going to have equation 1, which is x2 minus x3 is equal to 0. And then 3x2 minus 3x3 is equal to 0. This is still equation 1. We now have equation 4. Now what we can do is divide the entire equation 4 by 3, or multiply equation 4 by a third. That results in x2 minus x3 equaling 0. Notice that this will now give us the system x2 minus x3 equals 0, x2 minus x3 equal to 0. These equations are identical, which means one of the equations in the system is redundant. We can just get rid of it. All we're left with then is equation 1 from the system. This means that x2 is equal to x3. So we can set either x3 is our dependent variable, as our independent rather, or x2 is our independent. I will choose to set x3 as independent. So let's say that x3 is equal to some real number r. Notice that this automatically means that x2 also equals r, because x2 and x3 are equal. Let's take a look. We want to use either equation 2 or equation 3 to determine our value for x1. Let's take equation 2 simply because the x1 is already positive there. So we need to plug in x3. So plug x3 equal to r into equation 2. Notice that doing so will give us x1 minus 3r is equal to negative 1, which means x1 is 3r minus 1. Therefore, our solution set would be the set of ordered triples 3r minus 1, rr, such that r is a real number. That concludes this video on a review of systems of linear equations. In the next video in this series, we are going to begin to relate systems of linear equations to matrices. In other words, we're going to see how we can represent a system of linear equations as a matrix equation. So until that video, I hope you all have a good one, and I will see you all in the next one.